Talk about the ratio test and the root test. So these are two tests that we use to determine whether a given series is absolutely convergent or not. So consider the series a random series, sum from n equal 1 to infinity of a sub n. From the example that we have seen before, we know that for this to converge, the limit of an has to be 0. This is not sufficient, but it must be 0, because if it's not 0, then by the divergence test, it's not convergent. Now, we saw that the two series, sum from n equal 1 to infinity and of 1 over n, and sum from n equal 1 to infinity of 1 over n squared, these are two familiar series. We know that one of them converge and the other one diverge. Even though the two terms, 1 over n and 1 over n squared, both approaches 0 when n approaches infinity. But we need an to go to 0, but we need an to be to 0 quickly enough. This is the main difference here. Although both goes to 0, 1 over n squared approaches 0 much quicker than 1 over n. So sum from n equal 1 to infinity of 1 over n squared converges, while sum from n equal 1 to infinity of 1 over n diverges. So here's now the big question. Is it possible to know or to determine whether an approaches to 0 quickly enough? Okay, what do you mean by this quickly enough? Well, fortunately, yes. We do have two very good tests that will measure how fast a series approaches 0. The first test that we'll talk about is the ratio test, and it's given by the following theorem. So suppose that you have the series sum from n equal 1 to infinity of an. Then we will find this limit, L equal limit of absolute value a sub n plus 1 over a sub n when n goes to infinity. We have three possibilities. The first possibility is this. If the limit is between 0 and 1, including 0, excluding 1, then it converges absolutely, and this is very strong. Remember, we say that converge absolutely, this implies it converges. Okay? So, but we have more information in this case. We know that it converges, and if you take the absolute value of an, it will be convergent as well. Now, if L is bigger than 1 or L is equal to infinity, then the series is divergent. If L is equal to 1, then the test is inconclusive. We don't know. That means the test is not useful in this situation. Okay, let's do some examples to see how this works. So suppose that I have the given series and I want to tell whether the series converges or diverges. So we're going to use the ratio test here. So let an be 2. So I'm just calling this in this form. Remember, my goal is to find now this limit. It's all based on finding the following limit of the ratio absolute value a sub n plus 1 over a sub n when n approaches infinity. So if you just write this like that, that's limit when n goes to infinity. Write the meaning of an plus 1 and write the value of an. An is 2 to the power n over n factorial. An plus 1 is 2 to the power n plus 1 over n plus 1 factorial. Now, you can drop the absolute value. Why? Because all the terms that I have in front of me are positive. Okay, I don't have like negative 1 to the power something or a negative sign or whatever. So here, this is going to be the limit when n goes to infinity. I will drop the absolute value. At the same time, I'm going to use the division of two fractions as it's the first times the reciprocal of the second, like that. Again, here, before you take the limit, you can simplify. So remember, n plus 1 factorial, this is n factorial multiplied by n plus 1. So n factorial cancel with the n factorial. And 2 to the power n plus 1 times 2 to the n, this is 2 to the n times 2. Okay, That one is 2 to the n times 2, so 2 to the n cancel with 2 to the n. So basically, I'm left with this easy limit, 2 on the top and n plus 1 on the bottom, which is 0. And according to the theorem, this is L is equal to 0. That means it's absolutely convergent. This falls under the first case. So here are the steps that I just did. Again, let me repeat, we took the limit of this ratio. So I put the meaning of an plus 1, what does it mean, and what does an means here. Then I said drop the absolute value, and so on. So this is convergent, not only convergent, it's convergent absolutely. Here's another example. Determine whether the series converges or diverges. We're going to use the same idea. I'm going to let an be -1 to the n times n factorial square over 2n factorial. And then I will find the limit of an plus 1 over an in terms of the absolute value. So, you know, it's a bit complex here, but I mean, some stuff should cancel out. First of all, let's note something. Here I'm taking the absolute value of this whole thing. I can drop the absolute value under one situation here. This guy, when you take its absolute value, you're gonna get 1. Same thing, this guy, when you take its absolute value, you're gonna get 1. Okay, so this becomes as follow. This is 1, this is 1, so they don't appear right here, even though I did not remove the absolute value, but I can still remove it here. So if you want, we can just remove it. And I'm writing the first fraction times the reciprocal of the second fraction. So you can see that this becomes 2n factorial over n factorial square right here. Now, what happens? How did we go from here to here? Well, let's take a look at these. I got n plus 1 factorial square right here. Remember, n plus 1 factorial is n plus 1 multiplied by n factorial. Since I'm raising all this to the power 2, then this is equal to n plus 1 square multiplied by n factorial squared. So this n factorial squared will cancel with this n factorial squared, and you're going to end up with n plus 1 squared, which is the one that you see on the top right here. Now regarding the other one, I have 2n factorial here, and this is bigger, so this is 2n plus 1 factorial. So let me show you this here. 2n plus 1 factorial like this is equal to 2n plus 2 factorial like this. Let me expand this a little bit. You start by 2n plus 2, then the integer that comes before it is 2n plus 1. The integer that comes before it is 2n, and then you're going to keep going down, so this is 2n factorial. So that's why this guy right here can be written as 2n plus 2 multiplied by 2n plus 1 multiplied by 2n factorial. So this cancels with this. So in the denominator, I'm left with 2n plus 2 times 2n plus 1. Okay, now you can see that you have a rational function here. You're taking the limit of a rational function. The leading term on the top, if you expand this is n squared. The leading term on the bottom, when you multiply, this is 4n squared. Okay, because they have the same degree, so the limit will be the coefficients, like 1 over 4. Coefficient of this over the coefficient of this, 1 over 4. Now this 1 over 4 is the limit L. It's less than 1. So then the series is absolutely convergent. Another example, determine whether the series converges or diverges. Again, I'm letting an be n to the power n over n factorial. Now, here I want you to notice something. This is not some number to the power n. Like n is increasing, so the base and the exponent are increasing together. Okay, so you may see that this might diverge because the numerator is getting really big. let's see what's going to happen here. We take the limit when n goes to infinity of an plus 1 over an. We write everything like we used to do in the previous two examples. Then I will just write these fractions. As you can see, I'm dividing, so it's like fractions, so multiplying by the reciprocal. Similarly here, look at that one. This one is n plus 1 to the power n plus 1 over n plus 1 factorial times n factorial over n to the power n. This guy is n times n plus 1. Sorry, n factorial times n plus 1. So you can cancel the n factorial and factorial. You end up with n plus 1. Now, here, this is a bit tricky here. Look what's going to happen. You got n plus 1 to the power n plus 1 over n to the power n. Okay? So one thing I can do is this. I'm trying to get something to the power n. So, and I know that I have n plus 1 in the bottom, so I'm taking n plus 1 from here. So I'm writing this as n plus 1 times n plus 1 to the power n, as you can see here. Now this cancel with this. I'm left with n plus 1 over n to the power n. So it's like I'm finding now this limit when n goes to infinity, n plus 1 over n all to the power n. There's more than one way to find this limit. First of all, this is an kind of an undetermined form, because you will have 1 to the power infinity, and then we have a problem here. So one thing you can do is the following. You can write this as limit when n goes to infinity, 1 plus 1 over n to the power n. And I don't know if you recall that, but this is actually what E means. So E, so every time you have this limit, this is E. This is the definition of E, by the way. Okay, so E is defined to be this number, which is 1 plus 1 over n to the power n when n goes to infinity. This is the definition of the number E. So that's why here I got the E. Okay, so this is the limit of n plus 1 over n to the power n, and actually this is the main definition for the number E. So if you recall this from, I think we defined this in pre-calculus when we introduced exponential functions. It's E is the number defined by the limit of n goes to infinity of 1 plus 1 over n to the power n. Okay. So here E is bigger than 1. Because E is bigger than 1, the limit is bigger than 1. According to the theorem of the ratio test, this is going to be divergent. So the series diverges. Okay, this is one test. Here's another test, very similar, as you will see, it's called the root test. Okay, so the theorem is instead of taking the limit of an plus 1 over an, we take the nth root of an. And you can see something here that the results are very similar. If the limit is between 0 and 1, including 0, then it's converging absolutely as well. If the limit is bigger than 1 or infinity, then it's divergent. If L is equal 1, the test is inconclusive. So you can use either one of them, but from practice, you will be able to tell which is easier to use. Let me show you an example to show you where this is better than the ratio test. Okay, look at the first one. Okay, now the first one, this is an. So I can write it in a nicer way. I can write it like that. It's n squared plus 3n over 4n squared plus 5 all to the power n. So here it makes more sense to use the root test. So if I want to use the root test, so I will apply the root test. What I need to do is find the limit when n approaches infinity, the nth root of absolute value of an. So this is the limit. Why I'm thinking of using this better, because this is going to take the nth root, and since an has in the formula of an I have to the power n, so the nth root will cancel this, and then I'm going to get a simpler form. So that's going to be the nth root of n squared plus 3n over 4n squared plus 5 to the power n. So the nth root is going to cancel that one, so that's going to be just the limit when n goes to infinity of n squared plus 3n over 4n squared plus 5. And this guy goes to 1 over 4 as n goes to infinity, because that's a rational function with the same degrees. This is less than 1, so by the root test, this is absolutely convergent. So this is absolutely convergent. You see, it's very simple if you know what to use. Okay. Now the same goes for that one. Just use the root test. Okay, and okay, so for this one, let's call it Bn. So Bn is equal to n over ln n to the power n. Now, if I take the limit of the nth root of absolute value of Bn, then this is going to be the limit of absolute value of n over ln of n when n goes to infinity. Okay. Now here you have a problem because when you take the limit at infinity, that's going to be infinity over infinity. Now I can drop the absolute value because when n approaches infinity, n is positive, and ln of n certainly is also positive, because ln of n is positive when n is bigger than 1. So of course when n approaches infinity, this is positive. So this is the limit when n goes to infinity of n over ln n. Using the L'Hopital's rule, this is going to be the limit when n goes to infinity of 1 over n. So this n goes up, and that's going to be infinity. So this series is divergent. So this diverges, and the first one is absolutely convergent. Now we have seen all the tests possible. We have seen the ratio test, the root test, integral test, comparison test, limit comparison test. What else? I think I said integral test, alternating series test, and we know like the geometric series and the telescoping. So let's say that you are given the following. We're not gonna do them. We're just gonna try to see which one works best here. Like if you look at the first one, okay, so here the idea of this exercise is just determine which convergence test is best to use. If you look at the first one and you want to test it, I want to try something simple. So if I can do anything using the comparison test, I will. And here the comparison test will work. Okay, and you can use the limit comparison test with what? With Bn equals. So this is like my An. I'm choosing this to be my original term. Now, the highest degree on the top is n squared. The highest degree on the bottom is n cubed. So I will use it with 1 over n. It's like n squared over n cubed. That's going to work smoothly. The limit's going to be 1. It's defined. So they're going to both have the same divergence. So this is divergent. That's how you can tell right away. Now, for the second one, you know, I'll give you a tip here. Once you see n factorial, most likely the root test will be the best. The ratio test will be the best to use. Okay, so here, ratio test will be simple. You can try it. Okay. Now, that one actually, look, this is e to the power n. This is exponential. This is polynomial. Exponential is much stronger than polynomial. So this is not gonna go to 0. So here, verify, you need to use the divergence test, because the limit is not gonna go to 0. Use L'Hopital's rule 3 times, that the limit's gonna go to infinity. Here, you can see you have power n on the top, power n on the bottom. So this is like So an here is equal to something to the power n. So clearly if you use the root test, that's going to be very simple. Okay, so again, with practice and with experience, you will be able to tell which test is the best to use for every for a particular series. So here I have a strategy that I recommend for choosing a convergence test. First of all, you have to see whether the uh, given series is familiar. Maybe it's written in a different way. So try to take a deep look into the series, into the terms. For example, it could be equivalent to harmonic series, like a constant times harmonic or harmonic plus something. It could be an alternating series. It could be a P series. It could be a geometric series. Okay, so these series are familiar. We know them without testing. No need to test them. I mean, once we spot them, we know whether they converge or whether they diverge. So this is very important to do this at the beginning. Also, if you have, for example, if an is rational, like the first example, like the first one in the previous slide, in the first series in the previous exercise, it was rational. Once it's rational, okay, I try to compare it with a P series. Sometimes the comparison test is quick, but if you can't do the comparison test, the limit comparison test will surely work. Okay. Also, it doesn't hurt if you try to find the limit of an when n approaches infinity, because if it's not zero, then it's going to be the divergence test. Now, if it's alternating, you can use the alternating series test. You can also use the root test, or you can use the ratio test for it. It depends. Okay. Now, if the series involves factorial or other products, are often tested by ratio test. So ratio test is recommended when you see factorial. Now, if your series can be written as something to the power n, then root test would be the first thing to think of. Okay. Now, if all these they don't work, keep the integral test to the end, because we don't want to integrate and make things longer. Especially that if you want to use the integral test, you must first verify the 3 steps, which is continuous, positive, and decreasing. So if an is equal to f of n, and you know that integral from 1 to infinity of f of x dx is easy to evaluate, then you can use the integral test. So these are some recommended problems that you should be able to try. Indicate which test should be used for each of the following series. Okay. So just, you can indicate and you can test them as well.